and the process of data flow analysis and so on, to show you how exactly the backend process will flow and how the target code will generate it. So here we try to understand the basic target code generation process. We talk about a variety of optimizations that are possible, and we talk about little bit of memory binding and register allocation. Memory binding is what we have extensively seen in the module 6, runtime environment module. We little bit touch upon the actual translation to target code and its optimization. This outline you can see on the left hand side. So for target code generation, this is the basic, I should say, the basic input-output specification of the problem. For the discussion in here, I'm assuming an x86 32-bit processor. I mean, when I pick up examples of assembly and so on, or the registers, this is the assumption I'm making. But the discussions are generic and it will apply to all other types of target machines as well. The basic inputs are symbol table, which has been generated by the front end. And along with that symbol table, actually generically we call everything as a symbol table, but besides the symbol table we have talked of, where primarily the user variables and temporaries and functions are entered. In addition to that, there could be other symbol tables. For example, table of labels. If the program has used labels, then there will have to be a separate table for that. Table of constants, string constants and other data type constants. And of course, the quad array of the 3-address code. The total translated program that we have. So these are our inputs. So the first 3 tables we generically will refer to as symbol table, and then we have the quad array of the TSC. And the output, what we expect to generate from here, is a translation to assembly instructions. So it is a list of assembly instructions in the processor, and a different form of the symbol table, typically called the external symbol table, which will contain information that are required during and after the assembly process. That is during primarily the linking process, because as you know, the code could comprise multiple translation units, and we will do the translation as in the front end. In the back end also, we will do the translation based on the translation unit. So when we translate a unit, there may be symbols which are not defined in this translation unit. So variety of those information will need to be put in the external symbol table, so that the linker at the time of linking could make use of those and resolve those and create a single executable for all the translation units in the backend. Right? So this is our input-output requirement. And in terms of scope, I must emphasize that in this discussion, we are not talking about handling of errors or exceptions. Errors in terms of, say, if you in C, if you are using long jump kind of information, or you are using C++ exceptions, we are not discussing that, because they need, particularly the C++ exception needs quite some additional handling in terms of unwinding the stack when the exception is thrown, and making the exception exit not only back to the caller, but possibly up in the stream up to the point where there is a catch that matches with it. So it needs a little different or additional kind of processing, which at least in the initial discussion, we will not be talking about. So given this scope, let me just walk you through the basic steps in the target code generation. The first thing that we try to do, we have the quad array of 3 address code. The first thing that we try to do is to optimize it. As we will see that while generating the target code, we were primarily concerned or primarily driven by the syntax directed translation process. So which involves creation of several temporaries, and we have been very lenient in creating temporaries. Whenever we needed, we have created a new temporary and used it. We have been very lenient in terms of the control flow. I mean, whatever suits the syntax directed process. I will talk specifically with examples a little later. But in terms of control flow, you will see a lot of spaghetti flows happening in the translated 3 address code. So all of those or most of those can be optimized. In fact, things can be optimized beyond what comes in the common sense. So that's the first thing to do. So translate that into a code which is which use lesser number of temporaries, has less expensive operations to be done, has a simpler control flow, and so on. Once that has been done, then it is naturally, as you do this, the symbol table also gets updated along with it. Because if you find that a temporary is not required in the code, then certainly you remove that from the symbol table. And as you remove that from the symbol table, naturally the address computation of other variables which follow that will also get adjusted. Right? So once all that has been done, we have a final form of the symbol table. We need to create the memory binding. This is the basic process which we have understood in the real-time environment module, that we will need to create a layout of the activation record from the symbol table for automatic variables. We have to generate the static allocation in the global symbol table for binding the global variables, generate the table of constants, and so on. And what we have not discussed in the runtime environment module is memory binding may not necessarily happen with the memory addresses. It may happen with registers as well, because finally ALU operate with the register. So a variable in the program, whether it is user defined or temporary, could be bound to a memory address, as we have seen through the activation record, or it could be bound to a register, or both. So there is a major process of register allocation and assignment that will need to be solved as a part of the memory binding. I'm sorry. Once the memory binding has been done, then we will move on to the code translation. The code translation primarily goes from function to function. So in a function, and you will see this a little bit more during the Thursday's lecture by Professor Mitro, that there is a function prologue. That is, before you start the actual code of the function, there are few management code that needs to be put, which includes saving some registers, adjusting the base pointer, possibly initializing the activation record area, and so on and so forth. And also, after the function has finished the computation and it can actually return, there is an epilogue of codes which does the remaining adjustment to set every pointers back to its right position, or every register back to its right value, so that the control can go back to the caller. And in the middle is the actual function body, where you have to translate each and every quad, each and every 3 address code to the corresponding assembly. Now, once that has been done, now you have your program translated in terms of the target code, in terms of the assembly for our case. Again, there will be opportunities for optimization. These opportunities will arise for several reasons. One is it could be because of the different idiosyncrasies or different typical formations of the assembly language itself. There could be one 3 address instruction may have multiple options in the assembly to be translated. And we might need to change one option into the other. There would be a lot of, particularly, there will be a lot of load store optimization. For example, you see that you are loading a variable from memory into a register, and then actually you are storing it back, and you are again loading it without making changes in between. These things happen because of the process in which you go through the code generation, and those things can be optimized. And there are several other optimizations, so which is called the target code optimization. So there are multiple phases of optimization. Backend is full of optimizations, right? And finally, there will be different issues related to the target code management, because this is when finally you are generating the different assembly files for the translation units, and the final external symbol table and link information, which will be necessary for the linker for the multi-source bit. So this is the overall process. So I mean, till up to the end of the semester, we expect to cover different aspects of these in different depth. So let me just stop once and see if you have any questions. Any questions up to the overall overview of the process? Because now I'll get into the each and every one specifically and start taking examples. And while I present with the presentation on, I get blinded on the Microsoft Teams view. So if you have any question in between, please feel free to unmute yourself and ask me that question. Okay, it seems it is fine for now. So let me just proceed. Okay, so let me take you through each of these steps in a little bit more detail, starting with the 3 address code optimization. Right. So why do we need optimization? Because intermediate code generation process will have many inefficiencies, like extra copies of variable, which you must have experienced this by now. And where we use variables instead of constants, where actually it is a constant. We may be repeatedly evaluating the same expression and so on. So there are several inefficiencies that creep in, and the 3 address code optimization will have to address these inefficiencies and improve the code. And when we improve the code, naturally, any improvement you talk about, there has to be a cost associated with it. What are you improving? Because oftentimes, if you improve one parameter, another parameter may get affected. Naturally, the first priority, as we often see, is that of time, because we want to make the code, generate the code to run as fast as possible. which is common, which is what we talk about all the time. But the second, which often is very important, is space. And particularly as we operate in the era of, computing in devices of multiple form factors, particularly mobile phones and handheld devices and so on, which have very highly constrained amount of space, because it has to contain, it does not have a hard disk to keep your program files and so on. It has to keep the programs, your data, everything in the same SD card or the built-in memory that the device has. So even the size of a program might become a major concern. And there is often, you'll see that there is a trade-off between time and space. For example, if you're sorting the address book in a mobile phone, you would probably not go for quicksort, even though otherwise we have learned that quicksort is possibly the fastest sorting algorithm till design. Comparison-based sorting algorithm design. But you will not probably go for that, because quicksort needs quite a bit of stack space. It may be just okay to do an insertion sort or a selection sort, which is certainly complexity-wise is more time complex, but has much less space over it. And given the response time of the human who is working with the mobile phone, you really do not need that high speed of updating an address file. Whereas when you are working on the, say, the communication stack of the mobile phone, you would probably have to keep a close eye on the time, because while you're communicating with your base station and so on, the response time of your device has to be very, very fast as well. So, trade-off are there. And what has emerged very important these days is the requirement of consuming less power. So power complexity of code is becoming a very critical factor, and it is far more complex to analyze than the time and space, because time and space typically can be decided by each and every instruction. You know how much time an instruction takes, and you add them up. I'm just saying philosophically, you add them up, you get the total time. You know how much space every variable takes, and you add them up, you get the total space. But in terms of power, it is not necessarily only that. You cannot just add up the power consumed by the execution of every instruction. Yeah, okay, that's one factor. But power often depends, is a factor of changes that happen in the bits. If you do not change a bit, just hold on, then you don't consume power. But if you change a bit from 1 to 0 or 0 to 1, you consume power. So the power consumption is not only is a integrated sum of the power of instructions, but they are also a factor of the derivative, that is the changes that they induce, which makes the power analysis a lot more difficult. But code optimizations, keeping the optimization of power, is also becoming very, very critical. So these are the different cost factors that will happen here. Now it changes. One second, please. Now this this 300 code generation optimization naturally changes the structure of the programs, and sometimes even beyond recognition. Like you have inline functions. There will be unrolling of loops. We'll see what it exactly means. It will eliminate some programmer-defined variables also as unnecessary and so on. So it may become completely unrecognizable. Now, code optimization is not fully an analytical process, because as we'll go forward, we'll see that different code optimization techniques, we will try to define them in algorithmic terms as abstract problems, and many of them have been shown to be NP complete. So you know that their polynomial time solutions are not expected. Therefore, often you need to address several of these code optimization problems through a bunch of heuristics, and consequence of that is the percentage of improvement that you get on a program may vary. I mean, there may be, often there may not be a 100% guarantee of performance on the optimization always. In some cases, maybe you apply a heuristic for the optimization, and you may not be able to optimize anything. Even there are extreme cases where after optimization the code actually gets worse because of a wrong heuristics that you are using. And finally, the point that we will particularly start discussing in the next module, that optimizations may be classified as local or as global. And optimization is local if it is being done in a localized scope in the code, and it is global if it is being done in a total translation unit. For example, then there are optimizations which may be just done within a block or within a function, and obviously there are optimizations which are across multiple blocks and functions, multiple functions that exist in the translation unit. So these are the basic issues of the target 3-address code optimization. Now, specifically in terms of this TSC optimization, to optimize the TSC, the first very naive tool we have is known as peephole optimization. Peephole, you will understand, it's like a small orifice through which you can look at a little bigger view, but in a limited way, like it is looking through the keyhole of the door, kind of. So what you do in peephole is you just look at a couple of consecutive instructions, and based on the information that you see, you can optimize, can remove useless temporary variables, you can eliminate codes that are unreachable, you can do some flow optimization also. You can reduce the strength of some instructions, some operators particularly. So there are a variety of peephole optimizations which are relatively easy for a quick cleanup. Then there are optimizations known as common sub-expression elimination, where you find the same expression being evaluated multiple times and try to eliminate the evaluation of that expression after the first occurrence. Then there could be constant folding, that if you have expressions which involve only constants, then you do not need to generate code to evaluate them. At the compile time itself, you can evaluate them and put that resultant value. And very importantly, all these optimizations will lead to dead codes. Dead code means a code whose presence in the program has no effect. That is, it will not matter if you do not do that instruction. So when you have a dead code, you eliminate that. You remove that from the code so that the code becomes simpler, shorter, and obviously more efficient. And a very interesting fact about optimization is that it is not a linear flow. It is not that you will take the code, people optimize, eliminate common sub-expression, fold constant, etc., eliminate dead code, and you are done. Once you optimize, there will be, again, newer option or opportunities of optimizations that come up. So you keep on repeating till you come to a point where no further optimization opportunity are visible. Okay? So let us start with an example, and I will walk you through some of these optimizations based on this code. So please, you may actually take a screenshot and keep this code by the side, because we are going to use it all through the next couple of slides. So there are 3 arrays, A, B, and C, 2 variables, I, and a size n, which is set to 5, hard-coded. And then you have a for loop where if you go through, if AI is less than BI, which are input arrays, then you put CI as their product. And if it is not, then you set CI to 0. So it's kind of a vector product of AI and BI, but with a conditional difference. Now, in the next two columns, you see the translation. Though you have done the translation quite extensively, I will just still walk you through this to keep in sync. So when we start here, we have n initialized to 5. So this will generate a temporary T1, and T1 will be assigned to n. Then you start the for loop, I assigned 0. So another temporary T2 is assigned 0, I is assigned T2. So these are temporaries which are happening because of our translation process. Now, you might argue that I have been able to do this generation in a smart way so that I don't generate T2. Maybe you don't, but in some case you would, and in some other case someone else will generate this. But it is so. I'm assuming that you have this translation. Then you translate this conditional expression I less than n, which, as you have known, is a pair of gotos. First, a conditional goto, which checks for the condition, and then a unconditional goto, which is the false case. And after that, you have translation. So here, logically, after you have checked the condition, you actually should come and execute this if statement if the condition is true. So on true, you go to 109. Right? But this is fun of the syntax-directed translation, that syntax-wise, we get this if statement much later. Right? So we have to keep those dangling references and come back and backpatch them later on, as you have already seen. So the next code that would follow is basically I++. So you have a translation for I++. It is a post increment. So you need to retain the original value of I in T3, because at this point you do not know in the parse tree that whether or not this value will be used. So you have to keep that value and then increment that. And then again, so you will have all those m's in your translation code. So through the m.quad, you have to make sure that it does not fall through to the next. It goes to, after this has been done, it has to go back to that condition check again. So go to 104, it goes back to the condition. This has been backpatched much later, as you have seen in the translation of for. Then you have the if condition. Then you have the if condition check to be done here. So you have the translation for that. So to access AI, I think yesterday itself you saw through this that you are accessing an array element, and assuming that int has a size of 4 bytes, so your stride on the array is in order of 4. So actually, in terms of byte, the address is 4 times I, right? Because it's a size of, so it's basically size of the data type times I. So you get that index. So this is a byte indexed array A now, and you get T4 from that. So T5 actually is your AI. Similarly, T7 is your BI. And then you go ahead to do this condition check, which is T5 less than T7. And again, you have a pair of code for true and false. And the false part naturally keeps dangling, and you go to generating the code in 105 for CI assigned AI star BI. Now this is a straightforward code. T9 is CI, and then T11 is AI, T13 is BI. You compute the C first because it is on the left, so on the parse tree it comes first earlier. And then in T14, you multiply AI and BI and assign it here finally. And it realizes CI assigned AI times BI up to this point. And then you will again have to have a dangling reference, because you have to jump over this next and has to go back to do the increment of I. So it goes to 106, which is backpatched later on, to 106, where you increment I plus plus. If the if condition fails, then you go to 124, which is after this, where you again compute for the address of CI. Right hand side is T17. You assign that, and once that is done, again you are back to I plus plus. And finally, when I less than n fails, you jump over to 129. So this is the code that we have. This is what is given, and what we'll try to now take a closer look into is in this code, what are the redundancies that we have. Moving to the next slide. So this is just kind of a peephole optimization process. So in the peephole, I just keep on scanning the code, maybe looking at two consecutive quads together and see if there is something which can be improved. For example, we had T1 assigned 5 and N assigned T1. So we have a definition of T1 and had an use of T1 here. This is called def use chain. We will come to more details on that, but on this def use, since in people I can see whatever has been defined has been immediately used, so I can put that definition itself in the place of use. So I can replace T1 by 5. And if you have seen this code has been generated with the policy that every time you need a temporary, you create a new temporary. So you don't use a temporary. So which means that once T1 has been used here, T1 will not occur in the remaining part of the code. So after this def use propagation has been done, this one, T1 assigned 5, actually becomes a useless code because it is a dead code, because T1 is not used, it is being assigned 5. So we do not actually need to allocate location for T1 or actually allocate assign any value to that. Okay, so in that process, let's go forward. T2 assigned 0, I assigned T2. Again, the same def use can be removed. Then we come to increment of I, and you can see that here the pre-increment value of I, which you had to preserve because you were doing a post-increment operation, has not actually been used because it had to be used right here before you hit into this go-to. So that has not been used. So which means that this T3 is actually unused. It is not, not necessarily people will easily identify it, but this is something which we can see here. So this is unused. So this can be used. We can see this particular go-to at 114. It says go to 115. So it has happened to create a go-to to the next location, which is a fall-through location. So naturally, this is redundant. It will limit. In any case, it will fall through here. And if I go back one step, you see I have done some trick here. This was actually T5 less than T7, go to 115. Right. So this was a jump over a jump. 115 is the next instruction. So in the peephole, I see that it is a jump over jump. There is a jump 124. So I can eliminate this, the jump over jump, by just toggling the condition. So what I've done is I've toggled this condition. T5 less than T7. In the peephole, I've toggled this condition. I've made it greater than equal to. So if I toggle the condition, then naturally the targets toggle. So now on this, you are going to 124, or on this, you are going to 115, which is the next instruction, which is easy to detect that it will have no effect. So it can be removed. You have a similar def use propagation case in terms of T17 being 0 and start T16 being assigned T17. So propagate that, and this can be removed. So these are some of the very easy things. Then we observe something which is algebraic in nature. which is operator specific. That is, here we are computing 4 star I. Now, what is 4 star I? 4 times, which means that it basically is doing a left shift of I by 2 bits. That will always give us 4 star I. So, but the time taken to do a multiplication is lot more. It has to go through, as you know, a lot of steps, whereas shifting by 2 bits is kind of single cycle, because it's just a matter of shift register movement. Right? So I can change this 4 star I and have the same computation done as I left shift by 2 bits. Right? So that is called strength reduction. That is, I'm using a weaker operator to get the same result. Right? So these are some of the very quick optimizations that I come across as I see through the code. And since there are obvious def use related quads which can be removed, so I have assumed that they have been removed and I have renumbered outside. So you can say now originally what was 101 is 100, and originally what was 103 is 101, and so on. And I've shown both these numbers because these targets that we have for the go-tos are still with the earlier number, right? So this is a little bit of address management that needs to be done. So I'm showing both these addresses side by side. Okay. Now we have affected this, and with that, let me once go back to slide 10. So we can see that by this simple process, there were 129 quads earlier. Now we have 124 quads. So in the next slide, I clean up this, adjust the addresses and write it. So you have this new set of quads, 5 quads are gone. Now, so those are removed. The code is compacted, and I have done the strength reduction. So you can see at 6 places, there were 4 star I, which I have replaced with left shift of I by 2 bits. Right? So we have somewhat more optimized code. Now we make the next observation. And this is not necessarily peephole because this is not side by side. So we will need bigger analysis to get to this, and we will learn that more, but we can see this by observation that I left shift 2 has been done 6 times. And so if I have done it once here, do I need to do it? If I have done it at 106, do I need to do it again in 108? Or I can just use the value of T4 into T6. I can, as long as I does not change. And if, again, I go through this flow, you will see that the I changes only in 104. And this entire flow of whatever if paths you take will not hit I gets I plus 1. They hit it only at the end, after all this. So which means that once T4 has been defined as left shift of I by 2, I does not change over this entire of these 5 quads, whichever of them are executed. So basically, this is what is called a common sub-expression. So basically 2 conditions have to satisfy. One is, or 3 conditions I should say. One is the expressions have to be common, it's the same expression. And we are currently looking at just lexically same expression. Just to be lexically same expression. Second, from one expression to the next, or from the original expression to the next, the constituent variables of the common sub-expression must not change, because then I need to recompute it. And third is, this conclusion must hold on all possible control flow that can happen through the code. So we will come and formalize it. We'll form it in terms of a graph problem, and we'll do a solution for that. But I'm just talking about the intuition. So this is all that we can see are common. So which means that after this 106 has made T4 take the value of 4 star I in terms of this left shift, all remaining temporaries can actually use T4. So this is called common sub-expression. So I can eliminate common sub-expression by substituting T4 for all remaining. You can see here, I have substituted T4 for all remaining common sub-expression I left shift 2. Okay? And this is the reason which I've already explained. Now, once you have done that, you can see something interesting again. Say, if you look at 108, T4 has been assigned to T6. And then T6 is used in 109. If that be the case, then do I need to assign it to T6? Can I not? Like I did in case of earlier, as T1 assigned 5 and then N assigned T1, as I did. Can I not propagate this copy? That is, instead of using T6 in 109, I can directly use T4. Instead of using T8 in 112, I can directly use T4, and so on. So once I have done the common sub-expression elimination, then there is an opportunity to do, I'm going to the next slide, 13, opportunity to do a copy propagation. So I've propagated the copies, I'm sorry. So I've propagated these copies. T6, these 5 variables, I've made them all as T4 because they're same as the value of T4. Well, once I have done that copy propagation, now you can see that, well, what is the value of, what is the contribution of T6 being computed in this code? T6 is used only once here, and it is done, it is over. So T6 has no more, this has no further contribution to the code, kind of. So it means that it has become dead. So let us go to the next slide, 14. So these all have become dead code. All these 5 have become dead code because they are assignments to temporaries which are never used. So they can be simply removed. So I remove them. I've removed them. So these have now become blank. I've not done compaction, so I'm just showing it as removed. So there's no code as it. Now, as you have done that, you see that there is a new opportunity for common sub-expression. Now we have here between 107 and 114, you have the same expression 84. Right? And by that same logic that we used earlier, neither A changes, there is no assignment to A from 107 to 114, nor there is any change to T4. So none of the constituent variables change during this flow path. So whatever AT4 has been computed in T5, that same value will be recomputed in T11. So they become common sub-expression. Similarly, there's a second common sub-expression, which means that we can eliminate them. Going to the next slide, 16. So I keep these two and eliminate. I just copy, put T5 here, put T7 here. And as I have put that, T11 and T13, which were participating in code quad 117 to compute T14, these copies are propagated. You can clearly see the effect of this. If you have propagated this copy, T11 and T13 has no use. So they can be removed. I also observe another independent thing, which is N is assigned 5. And here I'm checking a condition if I less than N. and n is not used anywhere else in the program. So n is actually a constant in this program, though it is not defined to be a constant. So here you can see actually the benefit that our const declarations give to the compiler. If this were declared to be const int, which it could have been by the programmer, then we would have observed this even without analysis, and could have replaced any occurrence of n by that constant value 5. But here it was not done. Through analysis, we find out that n cannot change. Therefore, I can make this, okay, make this 5. This is called constant folding. And you can again understand the consequence of that, which means that n itself and the assignment of 5 to it is not necessary. It becomes a dead code. Next, slide 17. So we have 3 more lines of dead code. Okay. So we have several blank lines now, which are dead and has been removed. So this is on elimination of the dead code. This is how it looks like. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 quads have been removed and the program has been simplified. So again, I mean, since so much has been removed, I compact it from 101 to 124. I make it to 100 to 116. This is the compacted code that we have generated after this. And wherein you might start to think that, well, we are done. There's nothing more that can be done. But well, there's a lot that can be done beyond this. For example, one that we will discuss is very interesting way to do that is just look at I and T4 in this code. I is 0, T4 is not defined. I is with I being 0, you go to here, you defined T4. Right? I is less than 5, so you go here, you define T4, T4 is 0. So you have I 0, T4 0. Then when does I change? I change in I assigned I plus 1. Right? When the I changes, I assigned I plus 1, and you will come back to 101, 102, which is here, doing this condition check, and we'll go and define T4. So as T4 by I left shift 2, that is 4 times I. So if I increment, so and this is exactly keep happening in synchronization. If I is incremented, T4 is multiplied with this I by 4, which means that as I increments by 1, T4 increments by 4. You can see here. It's used here. As I increments by 1, you are doing 4 star I. So it's basically you are doing T4 assigned T4 plus T, T4 plus 4. So that T4 is 4 times I. Right? And they will always happen in sync, which means that you are having a loop whose iteration control has actually 2 variables, I and T4, which happen to change in a synchronized manner together. So these are kind of which is called loop invariant, that this property will not change during this loop. And therefore, I do not need to keep both I and T4. For that matter, T4 has a lot of use subsequently. So I can just get rid of this I and this computation. I can just start with T4 being 0 and increment T4 here by 4. And I will get rid of this I assigned I plus 1 altogether. As I get rid of this, my go-tos will get simplified. This will become just an addition. And I can just use T4 as my loop control. Okay? But certainly it takes a bit for a human to understand. So it takes quite a bit of analysis on the code to get to this point. Another point that I would like to highlight is you have a common sub-expression here, C plus T4, C plus T4. Now this occurs on 109, 112 on this quad, T9. And then you compute up to this and you go again. And this occurs here. Now, where do you come from? In terms of, if you look at this T5 greater than equal to T7, if it is true, you do this. If it is false, you do this. Okay? You can see. If it is true, you come to 113 and 120. Where you do T16 is C plus T4. If it is false, you also do the same thing. So what it means is no matter what is the outcome of this test, T5 greater than equal to T7, he will compute this. So what I can do a code movement. I can bring this C plus T4 before the test and remove it from here. Because I know in any case, I'll have to do this. And as I eliminate this common sub-expression by moving the code upwards, this elimination is not by using the computed value, because I cannot use T9 for T16, because if T16 is getting assigned, then T9 has not been executed. I said it has to happen on all control paths, right? And if T9 is being executed, then the T16 assignment is not happening. They're exclusive. But in that case, I can move this code up before the condition check and compute it in one variable, and then use that variable subsequently in both of these, which will mean that I will have a shorter code, and I will have a less, I have a less number of temporary to actually reserve, because T9 and T16 basically are playing the same role here. So this is called code movement. Again, it needs quite a bit of analysis of the control and data flow to be able to deduce this. And as we do this, then naturally we have a much again more optimized code. So these are certainly a little bit more advanced optimization, which needs all the tools of data flow and CDFG to be engaged in the proper way to get to this point. Okay. So this is up to, let me stop here. So and ask if there is any question. So I've just tried to show you that taking the 3-address code, what are the different optimizations that you can do either through peephole or through kind of a local reference, or in a more wider global reference all over the code, and drastically optimize. Actually, if you see that in terms of length, the code has become almost half. In terms of temporary variables, it is again become about half or a little less. And in terms of execution time, it has significantly improved, because lot of strength reduction has happened and lot of recomputations are already removed. Okay. So is there any, we'll come to the actual algorithmic processes of doing this in subsequent modules. I just want to I'm just making definitions of the different problems that we are going to solve. So is there any question on this? No? Okay, then we are the middle of the hour. So let us take a 5-minute break, and then I'll continue again on this, on the subsequent stages. Okay. Let us continue. After the three address code optimization, the next main part is to generate the memory binding, on which we already have had quite a bit of discussion. So I'll just do a quick recap and move on. So we need to generate the activation record. That is basically the layout of the activation record, offsets, based on the symbol table information for binding the memory for the local variables, automatic variables. So here we take a simple example where the function sum takes an array A and the size in terms of the number of elements. It defines two variables, initializes the sum variable to 0 and adds the elements of the array, and finally returns the result. So as we will go through and create the symbol table, we will have A, which is an array integer, which is a parameter, n is another parameter. Now this has a size 4 because an array is always a reference. So it's just an address, base address that you keep here. And then you have n, which has a size 4, and you keep on computing the offsets. I, S. T1 is a temporary that we have created. T underscore 1. So you can see sum gets 0, I gets 0, I less than n. Here is what you have generated, the T underscore 1, and those are, that is, I'm sorry. Here T underscore 1 is not a temporary. T underscore 1 is representation of this user variable to avoid confusion. T1 is actually the temporary. T1 is a temporary. T underscore 1 is a user variable T. And based on this, segregating the temporary and local and param in the structure that we have seen for the activation record, this is the kind of structure we will have, where in between, along this hash line, is where you will have the base pointer point. So this you have understood easily, and this transformation is not difficult to do from the symbol table to this activation record. Of course, it depends on what is your activation record data structure that you are going to use. So moving to the next slide, a couple of other things that you have to take care of is if there are global variables, then they will be put to the global symbol table, st.global, and their memory binding will have to be set in the data segment. Okay? The data segment is for the global variables which are not specific to the function and therefore will not go into the activation record. Similarly, those which are known to be constants, they will go to the constant memory segment. And then we'll have to create memory binding for variables using the registers. After a load or store, the variable on the activation record and the register have identical values. So we'll have to, that is a key observation. We always keep it in mind. And so we can use registers for the variables, and we'll see how to do this management. And it is often used to even pass integer or pointers to the function, or used to return integer or pointer values to the function. Of course, if your parameter is bigger than a register, then you will certainly pass it through the memory using the activation record. But if it can fit into a register, then you may choose to pass it through a register and have a better optimization. So these are the different kinds of binding typically for the global, for the constant, and for the params that you will do. Locals are taken care of by the activation. Now the question is, if I have to now find out the registers that I need for handling this variables, because the variables are in memory, whether they're in static or they're in automatic, that on the stack and so on. But certainly for computation, they will have to be loaded to the register, computed, and stored back. So what is important are, I've put 3 terms here, which is what we will learn over the next couple of modules. One is, I just talked about, is the def use. That is, when is that you define a variable and when is that you use the variable. For example, think about S. S is defined in 101 and is used in 109 and in 100, I'm sorry, used defined in 001. I'm not using 100 here. So S is defined in 001, used in 009, as well as defined. So it's this definition changes the original S. There's a use and then define. So the earlier definition actually ends here, and a new definition starts. And then finally, you have the use of S here in 11. Similarly, for I, the first definition is at 2. Second definition is at 5, where this definition of 2 is used, or actually the definition of 5 itself is used. So there is a loop. So the use and definition could happen. The same 3 address code could redefine, could use what it has defined earlier and redefine that variable. So this is what is happening. And this is another independent use, which may be of 2 or of 5. Right? So this way. So what we say is liveness. A variable is live if it can be used in future at any point in the code. At any point in the code, you say if a variable has been defined and is going to be used in future, then you say it is live. And after the last use of that variable, the variable becomes dead. So let's say when you start the program in this code here, at that point, A and N are your input parameters. So they are already been defined. They are live at this point. S is being defined here. So at the statement 0, S is not live. It has not been defined. But at this point 1, S has been defined, so it becomes live. And it will remain live all through because it is used up to the last point. Whereas I, which is live, which becomes live at 2, will remain live through this because you are going to use it here, going to use it here. Go to L1 at this point also, L1 is going back. So it has to be, I has to be live because it will be used. So you can see that future does not necessarily mean going forward in the code. It could be going backward in the code. Future is in terms of the execution. Right? So I is live here because it is going to get used at statement 5. So this is just a listing of variables which are live at different points. So T1 becomes live at 8. We are defining it. They use it at 9, and after that, this value of T1 cannot be used before being redefined. Right? So the life of T1, T_1, the life of T_1 is limited from statement 8 to 9. whereas the life of T1, the temporary, is limited from 7 to 8. Right? So these are at different points, what are the variables which are live. And we can visualize them in terms of what is called an interval graph. In interval graph, we on the x-axis, we put the statement numbers, and on the y, on the parallel axis here, we show the range of instructions over which a variable is live. So this shows that where it is. A is live from 0 to 10. S is live from 1 to 11. Whereas temporary T1 is live from 7 to 8, and so on. And this example does not show, but it is possible that I'm reusing a variable for different purposes at different points. So the integral graph or this line for a particular variable need not be a single line. There could be multiple intervals. And this is how they will be depicted. So what is this? One is this graph tells us about the liveness. The other is it will tell you, for example, how many variables need to be remembered at the same time. If you just draw a vertical line across this graph, the number of lines it intersects is the number of variables that are live at that point. So I cannot throw them away. So either I have to retain them in registers. If I want to retain everything in register, I need those many registers. Or I have to store them back to free the register. So I can say that this maximum is happening at 8, where actually everything 1, 2, 3, 4, 5, 6. So you will need up to 6 registers if you want to keep everything in the register. Otherwise, if we have less number of registers, then what we'll have to do, we'll have to sacrifice some value at a point and put them back to the store and again load them back. That's it. That will have overhead, but that is what is feasible in terms of the available registers. Right? So along with these variables, we will then have the registers also coming in and what values they have at different times. And this depiction is known as the interval graph. We'll see how to build them and how to analyze them and so on, just introducing the problems. So register allocation is a basic problem of, what are the variables that you put to registers, deciding on that. And certainly you need, if you have binary operators, then you need at least 2 registers to execute any code. And more registers you have, naturally it makes it easier. But you can decide as to how many registers you will actually use for keeping the variables. This is called the register allocation problem. And there is a subsequent question as to which variable will go to which register. If your registers in the processors are such that all of them, or at least majority of them, are general purpose, that any register can be used for anything, then you can use, once you have done the allocation, you can arbitrarily use registers for the variables. But if your processor needs that you will have operation specific register, that some registers can be used only for indexing, or rather some registers, many registers cannot be used for array indexing, only few can be done and so on, then that will put constraints on where you put a particular index variable in terms of a register. So allocation by itself does not solve the whole problem. You have to also decide on the assignment, to which register is assigned to which particular variable. So that is called a register assignment problem. So together it is register allocation and assignment problem. But mostly during reference and colloquially, we will talk about them together as a register allocation. And again, almost in any form, this problem and its variants, all variants are NP hard. So we will try to see a lot of different heuristic solutions to them. Now, once these registers have been allocated, now you can do a or rather, in order to allocate these registers, you need to perform a DFA. It is called data flow analysis. Whatever I shown here, I was, as a human, we were just tracing and saying that, okay, this is defined here, this is used here, this is not used after this, and so on and so forth. So data flow analysis is a bundle, it's kind of a framework where you set up a set of recursive equations, recursive definitions to define variety of properties. For example, liveness is a property, copy is a property. And you could set up recursive definitions for them and then solve that recursion. These recursions are basically recursions in terms of sets of three address instructions. So their solution is not arithmetically possible. So you have to do some kind of iterative solution and come to a least fixed point in terms of the solution to get to that. So data flow analysis is an approach in which you can do all of these in a manageable way and get all this information of liveness of the interval graph and all that computed easily. And you can then iterate through the liveness and use different heuristic to allocate register from the available register pool to each variable. The question actually arises when you run out of that pool. Then you need to decide which register you can cannibalize now, which variable you can cannibalize now, free up the register by storing that variable and reusing it for another variable. So this is the whole gamut of problems around this analysis and allocation assignment issues. Right, so this is just an outline of the steps, Kevin. We will come to this in detail when we discuss it in the module. Now, once registers have been allocated, load stores are now known, because whenever you have to put a variable to a register, you have to load. Whenever you have to free up the register, you have to store. So load stores are known. Now comes the rest of the code translation. So two parts of that translation are already you have seen through. One is the prologue of the function. So for translation, though there are several ways it can be done, but what we will follow is translate every function independently and then stitch the whole code together. So for any function, you need to set up the prologue code, which some part of that will be just, copy paste kind of like push EBP or move ESP to EBP and so on, which you have seen. Some will come from the size of the activation record and what registers you actually want to use, which caller had already been using. Right? So you have to push them. So this will have the function prologue part. Similarly, you will have an AP log part, as we have seen. You have to restore the registers and readjust the stack pointer and the base pointer and then the control pointer. Rest of it is basically mapping the three address code to assembly. And that's an extremely non-trivial problem again. Because how do you choose the most optimized assembly instruction to achieve what your three address code is supposed to do? So you will have further algebraic simplification. You will have strength reduction. For example, just to give you a hint, say we had in that code I assigned I plus 1. The question is, which assembly would you map it? Certainly, you can map it to an addition. So, which means that you use immediate addressing for the constant 1, and you use whatever register I is loaded in. So, you add 1 to that register and put it back to that register. That is one. The other possibility is the most assembly languages have an increment instruction. Whereas add may be 2 cycles, increment would necessarily be 1 cycle because it uses some additional logic to do that incrementation. So you may want to choose to use that increment operation over I assigned I plus 1. If it were I assigned I plus 5, you will not do that. If it is I assigned I plus j, you will not do that. But if it is I assigned I plus 1, then you might want to choose the increment operation. So there are a variety of such choices for simplification and reduction of strength. There are certain different machine idioms which may be of use. So you will have to look through all of these and do that. And once that has been done, then we will have to optimize the target code, eliminate redundant load store, eliminate unreachable code, again do a control flow. So, and as you have seen, like in the 3-address code, optimization is not a one-pass process. It will go through multiple passes, doing variety of optimizations, one optimization leading for the scope of other optimizations. And finally, you integrate into, because this was function-wise, so you integrate them into a single assembly file for the translation unit and generate the link information and prepend that usually on the assembly code itself. Now, before I close this module, just there's nothing much to discuss here, but these are just it's a very brute force and very inefficient way of generating code, but at least a feasible way to do that. That is, you can take every assembly instruction and instead of trying to do an optimized pick for the assembly, you can make a table for every 3-address code with the corresponding assembly. And instead of making a optimized choice, you can just do a table lookup. So these are the kind of arithmetic things, unary binary copy operators like A assigned 5, A assigned B. So you have written down what will be the assembly for that, and you will simply pick up from that table, put that code and keep on putting them together. As you can understand that every time, this code assumes that every time you are loading and loading and storing back. So A assigned B, you are loading the B into EAX register and you are storing it back to A. Whereas, if you are going to use that A, B subsequently, you may not have required this store. You could have just said that after you have loaded B to EAX, you could have just said that A is no more maintained in the memory. Its memory address is invalid because you are going to assign it. And its new address is EAX. So just by in your data structure itself, you can realize this assignment, which will help if, because it's very likely that if A has been assigned, it will be used. So subsequently, so if it is going to be used, then if you just know that it is available in EAX, that's enough. You can just use EAX till the point you need to free up EAX or change the value in EAX, well, you will actually do the store. So, but this is these are sequences which I have provided just to show you that you can do a brute force generation by doing load store everywhere. And then when you stitch them together, you will have a lot of unnecessary loads after store happening. So you can remove them through further processing. But this is just one way to get a code ready. Because it's certainly towards the end of your assignments also you'll come to a point when you have very little time left and you have to make something running so that you can finish the assignment. So this is at least one way to get your code working, though it will be very, very unoptimized. So these are examples of unary, binary, and copy binary operators and copy assignment. In the next slide, 32, you have conditional and unconditional jump. To translate all these go-tos and ifs and so on. Then you have the code for function call and return. And the final is for indexing of the array and the pointer. These are some specific codes in slide 35 for the double type, just to show you that how things differ when you deal with a different data type. And given that the assembly also has a support for it, otherwise you'll have to do all that management. Okay, so that was all that I had in this module. Before I move on, let me see what are the questions. Any questions, friends? So just try to give you an overall idea of the backend process. And next would be to actually go over each one of them through the proper data structure and algorithms to address them. Any questions up to this point? I hope everybody is awake. So let me move on. So I start with the first part of TSC optimization. And for that, I will first introduce the control flow graph and local optimization. So here we are trying to talk about code optimization, which I have already discussed at length. But the core part to learn here is what are basic blocks and control flow graphs, and what is local optimization, how to build a control flow graph, and how to solve some of the easier problems through DAGs and value numbering schemes and so on. So these are what this we have already discussed, that why do you need to optimize. This example is what we have seen, through which we have seen various different opportunities of optimization. So just to summarize, we have peephole, which can eliminate redundant instruction, local definition and use of temporary, locally unreachable code, jumping over jump, algebraic simplification, etc. We have seen examples of this. Then we have what is known as local optimization. Local optimization is something which happens within a basic block. We will just see what is a basic block. Basic block is something, it's a maximal set of instructions, consecutive instructions within which there is no diversion of the control. So if you start executing at one point, you'll have to end at the other point. And the maximal such blocks you can have are called basic blocks. So you can do this common sub expression within the basic block. You can propagate constants within the basic block. So it is a little bit, we are taking a little bigger peephole window, bigger keyhole than just looking at 2 or 3 consecutive instructions. Now we are looking at a longer run of instructions which are maximally straight line. And you can solve some of these problems. But majority of the real problems have to be solved globally, which is on the whole procedure or function or the whole program, wherein the control can go from one basic block to the other, and an expression defined in some basic block may be used in some other, and so on. Constants may need to be folded across. So all of the earlier problems need to be solved across a global scope now. And along with that comes some of the problems I highlighted, some of the opportunities I highlighted, like code invariance and code motion, and loop unrolling, vectorization, and so on. We'll come to those later. Now, coming to the basic data structure, the basic block is a unit, which is a sequence of intermediate code with a single entry and a single exit. And it has to be, what is not strictly put in the definition is the fact that it has to be maximal. Like you can say, would I take one instruction and say it is a basic block? It may be, but if a single instruction necessarily always have a single entry and single exit, but say A assigned A plus 1 may be followed by B assigned B plus 3, then both of them together have a single entry and a single exit. So you keep on increasing it maximally. When you necessarily have a point where you have a possibility of an alternate entry or possibility of an alternate exit, is where you stop and say this is the basic. And the control flow graph takes the basic blocks as nodes and show the control flow between them. So the basic blocks can be represented by directed acyclic graphs. We'll see. So here is an example. It's a very simple example. You can see it is doing a vector product, like it is a simpler vector product than what I had shown you earlier. This is doing a vector product. And you can see that prod assigned 0 is the beginning, I assigned 0, and after that, there is an entry from this backward jump. If you just look at this code linearly, there is an entry at L1, level 1, from this backward jump. So naturally, this basic block cannot continue beyond this because you will violate the single entry criteria. So you have to stop here in this basic block. Then you keep on going in this code, L1 to keep on going till you come to the if statement. When you come to the if, then either the outcome can be true. If it is true, you go back, or the outcome can be false. If it is false, you go to stop. So at this point, you violate the single exit criteria. So you say this basic block starting from L1 ends at this point. And then finally, stop is a one instruction basic block. So there are 3 basic blocks, and it has a simple B1 has an edge to B2, B2 has a self loop and an edge to B3. This is the simple control flow graph. Now the question certainly is, given a code, how do we compute the basic block? To compute the basic block, we compute what we say are the set of leaders. The leader is a first statement of a basic block. That is that is what is to be identified as a leader, because since the whole code is linear, if I can get the first statement of each basic block, then I'll obviously know the basic block. because any basic block will be from its leader to the next leader, not including it. Now, what can be a leader? Certainly the first statement of the program is a leader, because that is where the whole story starts. Any statement which is the target of a conditional or unconditional go-to is a leader. Because if it is a target like L1 we saw in the last example, then you have a potential entry at that point. And if you have a potential entry, then you'll violate the single entry criterion. So it is basic block has to start here. And naturally that target can be of a conditional go-to or an unconditional. So this is also a leader. So the second point comes from the single entry criteria. The third is any statement which immediately follows a conditional go-to is a leader. Any statement which follows a conditional go-to is a leader. Why? Because you have a possibility of a not single exit. Because if it is true, it will go at some point. If it is false, it will go at a different point. So the fall through of the conditional go-to is a leader. So once you have the leader, then all statements which follow it up to and not including the next leader is a basic block corresponding to that leader. Now, interestingly, this will also tell you that if you have any statement which has not been placed in a basic block by this process, then you can easily say that this can never be executed. Because basic block is finding out all single entry and exit points in the code and segmenting the code. So if one or more statements do not belong to any basic block, then there is no way to reach them and no way to get out of them. So they may be immediately removed if required. So here it is very easy to see. Prod assigned 0 is a leader because it is the first word of the program. So by rule 1. L1 is the target of a conditional go-to. So this is a leader by rule 2. And stop follows a conditional go-to. Stop is the next statement after a conditional go-to. So this is a leader by the third condition. So here we have a demonstration for all the three conditions. And now we do a linear scan starting from prod. You stop at L1, the first two forms the first basic block, L1 to the if, second basic block. So once we have the basic blocks, we make them the nodes of the control flow graph. Now one node which contains the first leader, the first statement, is the initial node. And then we put directed edges from one basic block to the other. If B2 can immediately follow B1 in some execution. So this will happen according to the conditional and unconditional jumps. Now, as a data structure, a basic block can be represented by the number of quads it has. We need a pointer to the leader. We need pointers to the predecessors of the block. Those tell me that if I have to come to this block, then what are the blocks from which I can come here? Similarly, the successors of the block. Right? So you can naturally think of these in the graph terms, the predecessor and successor relationship on your adjacency is what you will need to preserve. Then there may be several others that might be considered. So going back to our code, after the people optimization, So first quad, 100 is a leader. Then we have 102 as a leader because I have go to 102, so it's a target. 104 is a leader because I have in 109 go to 104, so that's a target. 106 is a leader because that's a target. And 120 is a leader because in 110 that's a target. 124 is a leader because in 103 it is a target. So by condition 2, I get 1, 2, 3, 4, 5 leaders. And then I have two conditional statements here. One is at 102, so 103 has to be a leader. And at 111 and 110, I have another conditional statement. So 111 has to be a leader. So these are my leaders, and now I'll go from here to here. 100, 101 is first basic block, 102 second basic block, 103 third basic block, 104, 105 fourth basic block, and so on. So this is the annotation. So now you can see this is the basic block 1, goes to basic block 2 by fall through. This is basic block 2, which goes to 124, basic block 7. You can see that alongside the quad numbers, I have started using the basic block numbers because the quad numbers give you the actual flow in the code. But if I know the basic block, then I can think of these as nodes, and these are basically these go to B7 is the edge adjacency from B2 to B7. So I have an edge from B2 to B7. Similarly, in block B3, I have B2 102, so I have an edge from B3 to B2. In B4, I just have a fall through to B5, and so on. In B2, I have something coming to B4, and so on. In this particular case, there is no unreachable quad, nothing to remove. So we have got this control flow graph from the original program that we have. And if you want to see it a little bit more graphically, then this is what we get. So the code, which was a linear structure, has now been made into a non-linear, which gives us the first advantage it gives us is the ability to work at two different levels of granularity. One is some of the analysis I can do within the basic block. I can take one basic block and try to optimize. For example, you can clearly see a common sub-expression here. Because whenever you enter this, you will have to exit through this. So there's no escape. So T4 is 4 star I. So T6 can be made T4 and then propagated. So you can basically remove in block B4, you can basically remove 2 and make this T4. So you can work at this. Similarly, there's common sub-expression, 3 sub-expressions which are common here, which you can optimize in B5. So you can operate just within every node. And that is what is called local optimization. But you can also operate across nodes. For example, as we have already seen, this 4 star I, which is common within the block, is also common across to B4, across to B6. So naturally, that you cannot analyze by working within the block. You have to look at the control flow and see that along this control flow, if I have defined it here, it goes to B3. I've forgotten to mark, or B3 is here. So sorry. It goes to B3, which changes I plus 1. And then it goes to B2, checks I, goes to B4, which gives you here. Now, the question is, so you will have to see that along this path, does it remain a common sub-expression? So that is a global approach. So the two set of approaches that will follow after this is basically a set of local approach and a set of global approach. So in this module, we'll talk about some of the local approaches which can be used within a basic block to optimize, and subsequently we'll go to the global approaches. I think before I go into the DAG representation of the basic block, let me stop here. There's not much time left, and see if you have any question up to this. So we have in this module, we have just introduced what is a basic block and what is a control flow graph based on the basic block. In the next couple of discussions, you'll see that basic block and control flow graph will become our core survival point. We will have to always work through them, with them, and solve a variety of optimization and code generation problems on them.
Sir?
Yes?
Why do we generate the 3-address code if we are just directly converting that to a CFG and then doing all optimizations? Can't we make the CFG from the AST directly? Or
yes, we can. Obviously, we can. See, basically, what do you gain by doing that? First of all, see, making the CFG from the quad representation is more an algorithmic process than a conceptual process. Right? Because you cannot make the CFG unless you have finished generating the code. You do not know where the targets will come from. As you can see, that the leaders to be analyzed, you have to go till the last statement to know that which statements, 3-address codes, are being targeted. Unless you know that, you do not know the basic blocks. So you can try to combine that with the AST-based generation, but that just it is just a little bit more complication. But yes, you can do that. I mean, you will always keep this in mind that this is an engineering problem. This is an engineering approach. So there are certain practiced ways of doing it, but there is not an absolute answer. This is not science purely. So you can choose to do it a little differently, but you'll have to ask that, do you really gain a lot? Whereas there is a significant requirement to separate out everything between the front end and the back end. Now, if you are saying that you are on the AST, I would say that it's same as being on the 3-address code. It's just a different representation, but it's necessarily the same set of information. Do you agree to that?
yes, sir. The information is of course preserved, but
it's the same. So the what you are saying is, why do I linearize and then come back and again non-linearize? That is your basic question. That I was on the graph. Necessarily, could I do certain collapsing of the AST so that every basic block corresponding part of the AST of the basic block gets collapsed appropriately? You can try to do that optimization, but it becomes, the problems are as such so complex that you try to usually want to have a simple, clean solution. Because as it so happens that these processes are pretty fast. So you really don't need to look at that kind of optimization, but that could make your programming complexity quite a lot. But conceptually, yes, and you can always go back to the AST and collapse things. But the moment you start doing peephole, you get into problem, because now you cannot work in the AST.
No, AST is definitely not good for optimization at all. It's
right. So you'll have to translate it back at some point. And as we'll see that three address representation, which is, see, it is looking so linearized because I am having to write it down on a piece of paper. But actually the three address, that quad, is actually a data structure.
Yes, so vector of classes.
So it is not that you'll have to spit it out to a file, which earlier people had to do, and then read it back again. It's not that. You are just doing a traversal. This traversal you can take is actually the program itself is the CFG. But only thing you are doing is you are doing some analysis, marking some nodes in that program, which are quad nodes. And then you are making hyper nodes in terms of basic nodes.
Yes.
Right. So actual implementation wise, you could look at it in there. But understanding wise, we need to go in steps so that at every point we understand what we are optimizing for, how we are optimizing, the correctness, the extent of optimization we get, and so on. Okay.
Sure.
Okay, then we are out of time. Thank you very much. Professor Mitra, is there any announcement to make from your side? Otherwise, we'll close.
No, it's fine. So I sent an email to all of them. The CT1 and LT1 marks are revised. And regarding Thursday's class, I will send another email that when it will start.
Okay. Thank you very much. Thank you, everybody. See you in the laboratory.